Okie dokie. So even though next week's material is going to cover really solving limits a little bit more algebraically, I felt it appropriate to kind of include this week, limits at infinity, because it is kind of a more conceptual concept to understand, and it's really not too bad. In the first video where I start covering limits, I talk about limits at infinity, and what I mean by that is a limit where, our input variable x is going off to infinity for some function. And I said we've actually discussed this before. You learn about it in pre-calculus 1, except your pre-calculus 1 teacher probably didn't use the word limits. And it was just kind of a way to say, look, where is our function heading to if I were to go on forever and ever and ever? And this is kind of useful if you are in the job of predicting, whether or not a business is going to thrive or it's going to decline, or if this is, revenue or maybe population growth or whatever it is. This is basically saying, if we left this function all alone and kept going for forever and ever and ever, as x approaches infinity, the question is, where do we end up, right? Where would this function end up? And some functions are really kind of easy to think about, because if I were to give you, say, the function y equals x squared, we can use our knowledge of two things. Number one, we could use the knowledge that the graph kind of goes up, up, up like so, and it's just going to keep going up, up, up as x gets bigger and bigger and bigger. And so we would have the notion that the limit as x approaches infinity of f of x would just, itself be infinity. And then, once we start incorporating calculus into this, then we start rewriting this as limit as x approaches infinity of x squared. And again, it is a conceptual exercise. It's like, what happens if I were to plug in infinity in there, right? What happens to the size of x squared? And the last time I checked, infinity squared is more or less just infinity. And so, we're going to get the same answer. It's just going to grow, 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 grow. So when we're talking about limits at infinity, some are kind of easy, especially when we're dealing with polynomials. Now, some may not have an answer, right? So some may not have an answer. For example, what if I give you the limit as x approaches infinity of sine of x, for instance? Now, this one's not so easy to do because, the function sine of x oscillates like so forever and ever and ever. And so trying to predict, hey, what is the output value of this function going to be as x gets bigger and bigger and bigger? Well, this is actually a problem because, the function sine of x oscillates between -1 and 1, and it does that forever. So, does infinity happen when we're at 1? Does infinity happen when we're at -1? Does infinity happen when we're at some point in between, or does this graph just keep going? And so ones like this, we would say dne, right? This limit does not exist, or it's also appropriate to say it's undefined, because we really could not concretely say one way or the other what value this sort of function is. But the purpose of this video is a little less, on the fringe cases like this, and more dealing with rational functions. Okay, and so as a reminder from pre-calculus, a rational function, rational functions, right? Rational functions look like this. It's some f of x over some g of x, where both f and g are polynomials. So this is a polynomial. I mean, technically, I guess it could be anything, but I'm going to start off with polynomials right now. So that's also a polynomial as well. And, as an example, right, we could have a polynomial function like x squared minus 3 over x cubed plus 7, okay? Now, with these sorts of graphs, okay, if you recall back to pre-calculus 1, there are essentially three things that could happen. Either our graph kind of goes down, right, and it would approach 0, or maybe our graph kind of grew and just kept growing, in which case it approaches infinity, or maybe our graph approached some value and we would get what was called a horizontal asymptote. And those were really the only three cases we could get when dealing with kind of the end behavior of rational functions. And that's kind of the idea here. You know, when we are evaluating the limit as x approaches infinity of some rational function, right? F of x over g of x. Okay, there are three cases. Okay, so let's take a look at this. So, case one. Okay, case one. The first case is that f of x is, I'm going to put it in parentheses, bigger, right? It's bigger than g of x, okay? And, you know, if we were to think about this, right? Let's say, you know, we're going to evaluate this, and f of x becomes monstrously big. And I'm talking like this goes to infinity while this thing is moving super slow. Well, hopefully you can imagine that in this particular case where f of x is quote-unquote bigger than g of x, the result is going to be that since the numerator is so large, we're going to get infinity, right? That we would expect whatever this graph looks like to grow in the long run. That's what we would expect. Now, case two is the opposite, right? Case two is that g of x is, you know, quote-unquote bigger than f of x, right? And when I say bigger, I mean like goes to infinity much faster. So I'm going to put goes, when I say bigger, I say goes to infinity much faster than f of x. It grows much faster. And if that's the case, right, if we end up with a case like that, then really what this rational function is going to look like is we essentially have like infinity on the bottom while the other one is still some number, right? Our first case was we had infinity on top and the bottom is growing so slowly that, you know, I'm still counting by numbers here while I've already reached infinity on the top one. And in this particular case, right, infinity divided by a number is just infinity, right? Half of infinity is infinity, a quarter of infinity is infinity, works out. Now, in this case here, right, I have something super duper big on the bottom and then something really tiny on the top, right? Like imagine I had 3 over 1 billion or something, or a trillion, or, you know, you just keep going, right? What would this equal? Well, if you pop this in your calculator, you just think about it, it's going to be 0.000000000, right? And it's going to keep going. It's something really small. And the idea is that if I reach, you know, theoretically, if I reach infinity in the denominator there, then this fraction, no matter what's on top, is just going to equal 0. So in this case, the result of the denominator growing way faster than the top is we're going to get 0 for our limit, which means that our function kind of goes like this and levels out at 0 in the long run. Now, case 3 is kind of interesting. Case 3 is the following, and it's where f of x and g of x grow kind of at the same at like the same rate, or maybe you know, I'll say they reach infinity. They reach infinity at the same time. Okay, and in this particular case, you know, you may recall that there is a special case where we don't end up with infinity as one of our horizontal asymptotes, and we don't end up with 0 as one of our horizontal asymptotes. And in this particular case, right, so what happens to this ratio over here? Maybe I have like, I have 3 infinity on the top, and on the bottom I have 2 infinity on the bottom. So, you know, part of it reaches infinity, they reach the infinity at the same time. And so in some sort of sense, those infinities kind of cancel, and you basically just look at these coefficients here, and you get, in this case, like 3/2. And so the idea here is that the result varies. Okay, the result varies, and it depends on specific coefficients. And what are those specific coefficients? These are technically the specific coefficients that we're going to be looking for are the leading coefficients. The leading coefficients of the function. And just as a reminder, right, a leading coefficient is like if I have 2x cubed minus x plus 6, the leading coefficient is the coefficient attached to the x value with the highest power. Right? So that's what we're talking about. And so I'm going to give a case of each one of these. So I'll zoom out a little bit to give me some writing space. So here we go. So example 1 for case 1. It would be like something like evaluate the limit as x approaches infinity of x squared plus 6 over 2x minus 3. Okay. Now, in this particular case, all right, how you deal with solving limits at infinity is the following. And it's a wonderful, wonderful little trick. The first thing you need to remember is that we are more or less comparing what's going on on top with what's going on in the bottom. That's what any fraction is. Okay, any fraction is just a comparison of what's on top to what's on bottom. So we're going to kind of consider, hey, what's going on here in the top? Now, the question that I'm going to ask you just really quick is, if we're talking about going to infinity, right, this graph on the top is a parabola, right? And my question for you is, if I were to scratch out this plus 6, would it change the end behavior of this graph? And by that I mean, if I scratch out this plus 6, is that all of a sudden going to turn it into a completely different graph? Is it going to change the shape of the graph? And the answer is going to be no, right? If I were to scratch out the top, on the top, this plus 6, I'm still going to have a parabola, and the end behavior is still going to be the same. And so what you can do is I can almost get rid of that while I'm trying to figure out what this limit is. Because on top, x squared plus 6 versus x squared, they're both going to infinity. And the x squared, the really important thing here is that the x squared is like the head honcho. It is in charge of dictating what is going to happen in this for this particular function here. And similarly in the bottom, right, I have 2x minus 3, which looks like a line. And in the long run, this minus 3 doesn't matter because I'm still going to have a line that's pointed up like that. And so it's like this term here that has the x attached to it is the head honcho. It's the one that's making decisions, that's basically saying, hey, look, we're a line and we're going up. And so trying to answer this question is the same, right? We're going to get the same exact answer as if we were considering the limit as x approaches infinity of x squared over 2x. Well, for this particular problem, right, in this case here, that means, right, the limit as x approaches infinity, we can simplify this a bit before I go to work. And I have this. And now I can evaluate this limit, and you might say beforehand, hey, well, why don't I plug in infinity here? And there's a reason for why we're not going to do it here. And because if I did, I'd get infinity over infinity, and it would almost look like, you'd be like infinity over infinity. That's just 1. But infinity divided by infinity is not necessarily 1 because there's different sized infinities. And if that's a hard concept to wrap your brain around, I like to show this example. So I'm going to take a small break from this problem and just go down here really quick for the idea of different sized infinities. And I would simply just ask you, technically, mathematically, this is incorrect, but I'm going to say it anyways, just kind of introduce this idea that infinities come in different sizes, which is if I were to ask you how many numbers are there between 0 and 1, you would say, okay, well, there's infinitely many numbers, right? And if I then asked you how many numbers are there between, say, 1 and 2, you would say that there are infinitely many numbers. So if I were to ask you then how many numbers are there between 0 and 2, would you say that there are the same exact amount of numbers, right? Would you say that it's just the same infinity? Well, that almost doesn't seem right because there's an infinite amount here and there's an infinite amount there. You would think, oh, well, it's got to be 2 infinity or something like that. And the reason why this example actually isn't the best is that technically speaking, it is the same size infinity. But the point is that you can kind of imagine that maybe from a more intuitive sense, if you've never kind of dealt with thinking about the sizes of infinities before, you can kind of think about this idea that that, here's like a small infinity, here's a smaller infinity, so this would be like an infinity that's twice the size. And the whole point is that, if I were to just plug in infinity here and get infinity over infinity, we can't evaluate this because I don't know, is this infinity twice the size, right? Should this be 2? Are these infinities the same size? Should this be 1? Is the one on the bottom twice as big as the one on top? Should I get 1/2? We don't know. Okay, and so to avoid that problem, we just basically keep doing some algebra to simplify things. But then here we kind of realize, oh, wait, if I were to evaluate this limit, aka I plug in infinity wherever I see an x now, I'm just going to get infinity over 2. And last time I checked, infinity divided by 2 is still infinity. Now, why does this answer make sense? Well, if you go back to the original question, and see if I can erase this without erasing the whole problem. If we go back to the original question, on the top of this problem we had x squared plus 6. And on the bottom of this problem we had 2x minus 3. And if I were to ask you, which one of these functions grows faster, right? Is it the one with the x squared, or is it the straight line right here? The answer, of course, is going to be that, well, x squared grows way faster than a linear equation. And so you can kind of reason it to yourself that this thing on top is going to reach infinity way faster than the one on the bottom. Or in other words, this thing is getting bigger and bigger and bigger and bigger, while this one is like slowly increasing in size. And so this limit, right, this ratio, if we were to compare them, is basically we're going to get something with infinity on the top and something that's still growing to infinity on the bottom, and that is going to give us infinity as an answer. So, that's going to be this first example. This is an example of a problem where we're going to get infinity as our solution. So this thing equals infinity. And now that we're kind of armed with that knowledge, let's kind of try another one. So for instance, what if I did the limit as x approaches infinity of x minus 2x squared, and in the bottom I have 3 plus x to the 4th minus x. Okay, what if I have something like this? Now, again, there's 2 ways to go about doing this. Okay, the intuitive way is to say, well, on the bottom, right, what is the degree of this thing on the bottom? Well, the degree of that thing, and we have an x to the 4th in the bottom, versus on top we only have, the biggest thing that we have on the top is that I have an x squared. And so which of these is going to reach infinity first? Which one is going to get to infinity first? The denominator is going to get to infinity first. Like, just intuitively that's going to happen. And so it kind of makes sense that this thing, right, when the bottom has reached infinity, the top is still going to just be some number, which means the bottom is humongous and the top is just a number. This answer is going to be 0, right? This limit is going to be 0. We would expect this rational function, if we were to graph it, to kind of do that and level out in the long run. Okay. Now, how do we do this a little bit more algebraically per se? We kind of take a similar approach that we did up here, which is I would say, okay, let's compare the function on the top, because that's what a fraction is. We're going to compare the function on top to the function on the bottom. And now, since we are specifically looking at when x goes to infinity, right? We're talking about in the long run. What is the shape of this graph? What term dictates the shape of this graph? Well, last time I checked, this is an upside down parabola, right? Negative 2x squared. And whether or not I have this x term in the front does not change the end behavior, right? The as x goes to infinity behavior of the top of this function. And similarly in the denominator, I have an x to the 4th here, which is my head honcho, right? That's going to be a pretty fat looking parabola here of some sorts. And whether or not I have this minus x term or this 3 term here doesn't change the fact that my end behavior here is going to be shooting up courtesy of the x to the 4th. And so it's, that means we're going to get the same thing as if I was evaluating the limit of negative 2x squared over x to the 4th. And again, we can simplify this a little bit before we plug in our x going to infinity. We can say, oh, so I get negative 2 over x squared. And now we can say, okay, well, let's pop an infinity. I'm going to get negative 2 over infinity squared, which is just infinity. And here again, I have some number over infinity. That's just going to go to 0. And so in this particular case, we're going to get 0 out, where the denominator here is bigger than what we had in the numerator. Now, case 3 is the fun one. So case 3 isn't going to be too bad for us, though. So let's do an example where I have like the limit as x approaches infinity of, negative 3 plus 2x squared. And on the bottom, I have 7x squared minus x minus 1. Now, in this particular case, if I were to ask you which of these functions, the top function or the bottom function, is growing faster, right, as x approaches infinity, it's harder to say because both of them are quadratics, right? Both of them have a degree of 2. And so in this particular case, if we go through and say, okay, well, let's look at the top. What thing doesn't matter on the top? Well, this minus 3 doesn't matter on the top because the 2x squared is dictating that this is a parabola. And similarly on the bottom, the minus 1 doesn't matter and the minus x doesn't matter. And people usually have a qualms with this. They say, well, Dylan, x is infinity. Like you're saying that this infinity doesn't matter. I'm saying, yeah, because in the long run, right, whether or not I have it, I'm still, right, this infinity squared is going to be way more important and have way more weight than this little minus infinity here. And so, we can get rid of this minus 1, we can get rid of this minus x because the bottom itself is still dictated, its end behavior is dictated by that 7x squared. And so once we scratch these out, we get the limit as x approaches infinity of 2x squared over 7x squared. And this is just the limit as x approaches infinity of 2 over 7 because all these x's canceled out. And now we can evaluate it. Let's plug in all the x's. Well, there are no x's to plug into, so we can just do it and say, okay, well, there's our answer. Our answer here is 2/7, right? What is the limit of 2 over 7 as x approaches infinity? There is no x to change the value of this, right? The answer is just 2 over 7. So we'd expect that in the long run, whatever this graph is, it could be super wild, but it's going to level out at y is equal to 2 over 7 in the long run. And so that's it. These are the cases. There's 3 cases. You learn about them in pre-calculus. You learn if the degree of the top is bigger than the degree of the bottom, or if the degree of the bottom is bigger than the degree of the top, or if they both have the same degree, right? If they're both the same size, then you look at the coefficients. That's the way you learn it in pre-calculus. But now with limits, we can kind of understand a little bit better why that is the case. And I think as a bonus example, a little bonus example would be, how do you tackle one that maybe doesn't look so straightforward, right? What if I have the square root of 3 minus x to the 5th plus x squared, and then in the bottom I have x cubed plus x plus 7. And have something like this. You're like, ooh, terrifying, right? Now, in this particular case, right, evaluating limits at infinity really just boils down to, which of these things is larger than the other one? Is the thing on top bigger or the thing on bottom bigger, or are they both the same size? And for the bottom, it's not too bad, right? If I could rewrite this limit as x approaches infinity, and I could, keep my square root 3 minus x to the 5th plus x squared over just x cubed, right? Because in the bottom, the plus x doesn't matter, the plus 7 doesn't matter. We're talking about being at infinity. Cool. And kind of in the same way, in the numerator, right, in the long run, whatever shape this is, the x to the 5th, and specifically minus x to the 5th, is going to be the thing that, actually, I guess I shouldn't have a minus here because this thing's going to be super duper negative and we can't take the square root of a negative. So let's modify this example just to be positive here, because that's how math works. Not everything works all the time. We gotta make stuff up. Math is pretty much entirely made up anyways. But the point is that this x to the fifth term is going to be the thing that's in charge of everything, and that this plus x squared in the long run and this plus 3 here isn't really going to matter. And so we can kind of just view this as the limit as x approaches infinity of the square root of x to the fifth over x cubed. And last time I checked, the square root of x to the fifth is the same thing as having x to the fifth raised to the 1/2 power, which is x to the 5/2. And if you, God forbid, need to use some decimals, you can think about that as x to the 2.5. And so this limit, as x approaches infinity, I'm not going to use decimals. I don't like decimals. I'm going to leave it as x to the 5/2 over x cubed. But we've now come to the conclusion, which is, well, the denominator is clearly bigger, right? It's going to get to infinity much faster than whatever we have there on top, because the degree of the bottom is larger than what's on the top. And so in this particular case, we still end up at 0, because the bottom is going to grow to infinity faster than the thing on the top. So yeah, that's it. This is limits and infinity. This is trying to incorporate the idea of horizontal asymptotes that we learned about in pre-calc 1, or what we would call the end behavior of functions. Then there's a few cases for dealing with this. There's more cases and there's different functions, but we'll handle them all next week. This week is simply just kind of an introduction to this topic, and dealing with some relatively simple examples with rational functions. So hopefully this was cool and interesting, and you're intrigued. And then when they're up, we'll head on to the next videos on solving limits algebraically.